Okay, guys. And this part is our last part in this topic, or in this syllabus, talks about radioactivity and nuclear radioactivity, atoms, nucleus, and so on. And I will start with very simple stuff. حتى even guys, these things were covered in grade 10 in O level. You know this atomic model. The atomic model consists of nucleus that has protons and neutrons. In the outer shells, we have what? Electrons. Nuclide notation, you know that. Any atom can be, or any element can be written like this: X, Z, and A, where Z is the atomic number, which is equivalent to the proton number. A is a mass number, which is called also nucleon number. You know that Z is equivalent to number of protons in the nucleus, or even electrons command, same thing. Or represents that. Mass number equals to the number of protons and the neutrons. The sum of protons and neutrons. Number of protons plus number of what? Neutrons. There is another definition which is called the nucleon. I think all of you are familiar with this. The nucleon, guys, protons and neutrons are called what? Nucleons, right? Protons and the neutrons are called what? Nucleons. Well, mass number here, guys, and in another word, the mass number and nucleon number are the same. Also, here we have to define something called isotopes. And guys, the isotopes are atoms of the same element, but they are differ in what? Number of neutrons, right? Differ in the number of neutrons. They contain different number of neutrons. Here's several examples about these things, like helium 3 and helium 4. Here, guys, we have a notation. In this notation, we wrote always in mass number. Right? والelement simple guys. اوكي element ايش simple؟ يعني طلع هون لما نكتب مثلا helium 3 here or helium 3 in this way or in this way, no matter. Well, this means, guys, that the mass number is 3 here. Mass number is what? 3. If I wrote it like this means that the mass number is 4. Or a nucleon number is 4. This is the way that we distinguish between isotopes. All elements طبعا found is a mixture of several isotopes. هلا chemical properties, guys, for isotopes is ايش? Are the same. Okay, but they change. Oh, sorry. They different in the physical properties, right? They are different in the physical properties. هلا natural proportion, guys, of isotopes are expressed in the form of an appendance ratio. بسموه appendance ratio. I think you took that in chemistry. Appendance ratio, the percentage of this isotope in the matter, or in the existing in the universe. for example, about the dependence ratio, let's consider, let me close this. Okay. If I consider uranium, guys, if I consider the uranium, uranium has two main isotopes, uranium 238, uranium 235. This dependence ratio 99.9, I think 3%. Well, dependence ratio for 235 is around 0.007%. Yani any sample of uranium, I will find 99.93% uranium 238, 0.07% of 235. This is called dependence ratio. Here, guys, also another concept here, which is nuclear force. And the nuclear force, guys, it's a force that would be used to hold to hold the nucleus compartments together, because you know that inside the nucleus we have protons, the force between the protons is a repulsive force. Since they are very close, this repulsive force is extremely high, but the nuclear force is stronger than this repulsive force. So this nuclear force will bound protons and neutrons together, tightly together in the nucleus. The force, it's the strongest force in the universe. It's always attraction. Guys, it's independent of charge. It's independent of charge. Yani proton inside the nucleus. Inside the nucleus, there is a force between proton and proton attraction. This is not not electric force. This is what? A nuclear force. And beside the electric, there is also a nuclear force. But this nuclear force, guys, it's called short-range force. So this force, this force is applied only for when the protons are very close together. Also, proton with a neutron, there is an attraction. Also, neutron with the neutron attraction. Even the neutron is neutral, it experiences a nuclear force, since this nuclear force is independent of the charge. And this force to overcome the repulsive force between the protons. Here, guys, this is a very important thing, the mass of a nucleus. To find the mass of the nucleus, we have something called unified mass. This unified mass, guys, it's approximate mass of the nucleon, which is 1.66 times 10 to the power negative 27, which will be given to you, okay, in the formula, in the data sheet. If I want to find the mass of any nucleus, I have to multiply mass number by U. Okay, yani the mass of uranium-238 is equivalent 238 times 1.66 times 10 to the power minus 27. Right? So this is the mass, or in this way we can find the mass of the nucleus in 10 guys. Here I think also you are familiar with that, radioactivity or radioactive decay. Guys, in general, the nuclei can be classified two parts or categorized in two categories here. Stable nuclei or unstable nuclei. Okay, guys. طبعا later on next year if you'd like يعني بعيد الشر اللي بحب فيكم ياخذ ال A2 بيعرف شو الفرق بين الستيبل والانستيبل. هلا الانستيبل guys nuclei want أو these nuclei want to be stable or aim خلينا نقول tend to be stable, so they will do something called decay in order to become more stable. I give example like this. No, if there's a classroom and in this classroom there are some of troublemakers, let's say, roughly speaking, if I can say that. If the teacher did everything to discipline the class, finally, if he cannot do anything, he applied strong nuclear force, he applied everything, but his force, let's say, is not enough to discipline the class. What he has to do, therefore, he has to kick some of them out of the class. This is what is meant, or this is the same thing as the decay. Decay, guys, something called disintegration. And part of the nucleus, or certain thing of the nucleus disintegrated from the nucleus. As a result of that, the nucleus becomes more stable. Accordingly, guys, here we have a parent nucleus. After a decay, we will have two things: a daughter nucleus, the new nucleus, and this is called radiation. The part, let's say, if I can say that, the part that is kicked out from the nucleus, it's called radiation. Right? It's called what? Radiation. This is a good simulation, guys, for the radioactive decay. أول decay, guys, أو أول part بسموه alpha decay. Here, guys, if you can see, these are unstable nuclei. This is a simulation. The red here, or the red spheres represent protons, while yellow spheres represent neutrons. Here, guys, after this decay, if you see here, part of the nucleus disintegrated from part of the nucleus is disintegrated from okay. If you see here, guys, this is unstable nucleus, right? Part of this nucleus will disintegrate from this nucleus. This part consists of two protons. Okay. This part consists of two protons and two neutrons. The part that, guys, that are disintegrated from this nucleus is called alpha particle, or helium nucleus, because it consists of two protons and two neutrons. That's complete. The second one is beta decay. Look here, guys. What is going on here, guys? If you watch this carefully, here one of the neutrons changed to protons. One of the neutrons, sorry, changed to proton. It was yellow, then it becomes red. Pay attention here, look. One of the neutrons becomes proton, and something else is emitted outside the nucleus, which is electron, or very fast electron, or energetic electron. As a result of this, guys, electron is emitted outside the nucleus. This electron, guys, is called beta. This electron is called what? Beta. Clear? Last radiation or last decay gamma emission. As you see here, first of all, alpha is emitted here, right? If you observed, then look to the nucleus now. What will happen to the nucleus? Guys, if you see here the nucleus after emitting alpha or beta, it may or mostly it become excited. Excited means it has, or this nucleus has a very or has high energy. Okay, has high energy. In order to release this energy to become more stable, it will release it as electromagnetic radiation, which is called gamma ray. High energy electromagnetic radiation or higher frequency electromagnetic radiation, which is called gamma ray. This gamma ray, guys, this gamma ray is emitted from the nucleus to release this energy. If you see that the nucleus was unstable, right? The nucleus was unstable. So here, these are the three types of radiation. We'll talk about them later also in more details. Any element, guys, here, any element here, any element that emit radiation, any elements that emit radiation is called radioactive material. The common example, uranium, radium, polonium, these things. Radioactivity is measured in becquerel. The becquerel, guys, shows how many decay we have per second. There are three types of radiation as what we discussed: alpha, beta, and gamma. Okay. Let's talk, guys, about the properties of this radioactivity, or properties of radioactivity. First property, guys, radioactivity is a random process. And there are several questions in the past paper that ask you about what is meant by random process. It means, guys, that the radioactive sample, one, cannot predict which atom nucleus is going to emit radiation at any particular time. But the probability of emission is constant. And if you are asked about these things, you have to write this point. First mark, the second mark, probability of the emission is constant. What does this mean, guys? If I consider a sample, this sample has several unstable nuclei like this. Okay, so let's say the probability for radiation is a 3 decay. Okay, خلينا نقول أو 3 atoms that decay per second, per minute, whatever, no matter. Let's say these are the first atoms that decay. This is, let's say, these 3 decays in the first second. In the next moment or in the next second, I don't know. I can't predict which atomic nuclei will decay. And I can't predict that this atomic nuclei may decay, or this one, or this one, or anyone. And I may have like this. okay, and so on. This is why it's called a random process. This is why it's called a random process. As a result of that, guys, as a result of that, when we detect the radiation, right? And if I make a detection for this radiation, it will not be constant. Yani the reading will keeps going up and down. I will show you that. Okay, the reading as a result of that, the counts or the reading that will be taken using a detector will be slightly fluctuated. Okay, to get an accurate reading for a background or for any measurement, I have to need or we need to calculate the average value. Yani I may measure the reading, let's say like this table. Here time, here counts. I will explain that for you later on. First minute, second minute, third minute, and so on.
بتاعت هما مش بالاور السكندز قصدي
Hours, seconds, minutes, it depends on your ايش. It depends on
على
حسب انت ايش.
الماتيريال اللي عندك.
طبعا اكيد حسب الماتيريال definitely. يعني here I may get مثلا 39, 41, 40 مثلا and so on. So they slightly this is called fluctuating or slightly changes. Okay, so here in order to find the counts for example per minute, I have to take an average. Yes. Yes, عويد حبيبي.
كيف بتقل third minute كيف قلت عن second minute
هو
كيف المفروض
لما احنا regularly وين بنحط الديتكتور مثلا let's say انه انا I placed the detector here. هلا if I consider that guys, not all of the radiation alpha, beta or gamma will reach the detector. You got my point? يعني these, let's say these radiations that are emitted here will not be detected by the detector. So here guys we will observe a slight variation in that. I will show you that. Okay. Radioactive material, guys, or radioactivity, this process also, it's a spontaneous process. What does this mean? Yani I can't speed up or can't speed it up or slow it down. Yani let's say if the rate of decay is 3 becquerel, it will stay 3 becquerel even if you heat the sample, if you put it under the pressure, if you put it in a colder region, or if you reduce its temperature, same thing. So this process is independent of environmental conditions or any other external factors. Okay, any question about that? So it's a spontaneous result, natural process, so it cannot be speed it up or slow it down. Third definition or third point here, guys, I have also to define background radiation. I think most of you familiar with that. You know, now around us, guys, there are radioactive materials everywhere, but this radioactive material has a low intensity of radiation. Have low intensity of radiation. So this radiation, guys, very low. So our body can tolerate with this. Here we have some examples. Earth crusts also, guys, radiation that are emitted from Earth's crusts. Radiation from outer space. Emission from nuclear experiments away from us. Also, part of this radiation may reach us. Building material. Radon gas in air also might be a source for background radiation. Guys, when we detect and measuring the radiation, first thing that we have to do, we have to subtract what? The background. We have to subtract what? The background. He placed مثلا detector here. This is a detector. This detector is switched on مثلا for 3 minutes, let's say. Okay, without a sample here. And he recorded the background or average بتاعت background counts. Then after that, he placed here the sample or the radioactive material. Here, guys, the detector in this position without the sample will measure the background. Okay? Okay. Radiation, مثلا, if you consider the interval to be 1 minute or 1 hour, whatever, you will find that there is a slight change or slight difference between these values. عشان هيك احنا بنحكي عنه fluctuation. اوكي بنحكي عنه ايش fluctuation يعني الفاليو fluctuate يعني بتكون ال readings keep up and down slightly changes. Ionization, guys. هلا ال concept of the ionization انه you know the definition of ionization also you'll be asked about these things. Ionization as a concept when atoms lose or gain electrons. Now, how do radioactive radiation? How does the radiation cause ionization? Let's say I have here atom. Consists of what? Electrons and so on. This is the nucleus. Here we have electrons. Let's say these atoms are exposure to radiation alpha, beta, whatever, gamma, no matter what is the type of radiation. As a result of this collision, guys, between the radiation and the atom, the radiation may knock off one of the electrons or electrons from the matter. Right? Eventually here I will have ions plus what? Electrons. Right? As a result of this collision between the radiation and the atoms, electrons are knocked off from the atoms, so we will have ions and electrons. This is called the ionization that is caused by the radiation. This ionization depends on the size and the mass of the radiation. Okay, size and the mass of radiation. The one that has larger mass or larger size, like the alpha, will have higher probability to collide with atoms and higher momentum as well. So it has a higher ionization effect. I think most of you also will be familiar with this table. In this table, guys, we have to distinguish between these types of radiation, and you'll be asked about these things. First of all, alpha as a nature, as what we mentioned before, guys. Alpha is a helium nucleus, made up of two protons and two neutrons. If you write in the external or in your exam helium, it will not be credited. It will be only you have to write helium ion or helium nucleus. Beta, this is the new thing that we did not talk about it in the previous year or in the O level. Here we have, guys, two types of beta: beta minus or beta plus. Beta minus high energy electrons emitted from the nucleus. هلا في عنا شيء بسموه positron or anti-electron. Okay, the positron same as the electron except the charge, and the same mass, but it has different charge. فهذا بسموه positron أو beta plus. يعني هلا احنا عندنا two types of beta or two types of beta radiation, either beta plus or beta minus. Either either electrons are emitted from the nucleus or positrons are emitted from the nucleus. Pay attention to this point, guys. Why these electrons are called beta? Because we have to distinguish between the electrons in the outer shells with electrons that are emitted from the nucleus. These electrons that are emitted from the nucleus as a result of radiation, they are called beta. اوكي. البوزيترون جايز هو انتي ماتر اوف الكترون. طبعا التشارج تاعته اتفقنا راح تكون ايش؟ فلانه بالاخير بتحول ايش ثاني. هلا الجاما بتعرفوا هي هاي انرجي او فريكونسي، لا تنسوا هاي انرجي اند فريكونسي الكترومagnetic ايش؟ راديشن. الماس طبعا الالفا هي الماسيف 1 compared with others، بعدين بيجي البيتا، بعدين الجاما. الريلاتيف تشارج هذا التشارج تاعته بوزيتيف 2 الكترونز، هذا النيجاتيف 1 الكترون او بوزيتيف 1 الكترون حسب اذا كان بيتا ماينس او بيتا بلس. السبيد الالفا تقريبا 10% سوري 10% of speed of light، البيتا 90% of speed of light، والجاما speed of light. Here guys الانرجي الالفا has discrete values of energy, right? Discrete values of energies. Here we have continuous range, وهي discrete values of energy. Ionization حكينا highest ionization هي الألفا، البيتا less ionization لأنه هاي، والجاما least ionization ليش؟ لأنه عندها هاي massive. هلا فينا إيش اسمه penetration effect أو penetration power. I think all of you familiar with that. إنه الجاما has the highest penetration power because its mass because gamma is massless. It can penetrate everything. Alpha only our skin or a paper, thick paper, صح? Is enough to block alpha. Beta can be blocked using a metal sheet, or thin metal sheet can be used to block beta, either positron or electrons. You know that we need a very thick lead or very thick concrete to block gamma. Guys, thick and thin, this is also a very important point. You have to mention it while you are answering the questions. هلا الeffect in electric field, you know that. Effect in electric field, guys, you know that. This is an important point because we took the electric field. البيتا guys, البيتا negative, صح? Is deflected towards the positive plate, right? Alpha will be deflected towards the negative plate. Also البيتا ايش؟ positive، بس برضه بيكون عندها higher deflection. higher ايش؟ deflection. الالفا
فيها ماسف
compared طبعا احنا
مش ماسف.
لما اقول massive compared with other radiation طبعا اكيد. ف it will have higher deflection. Less deflection. البيتا less mass او has البيتا particles have less mass than الالفا, so it will be deflected اقل. الجاما طبعا it will not be ايش deflected. هلا هذا البارت صراحه ما اتوقع انه حجيب عليه اسئله ابدا، يعني هذا الليفت هاند رول مش مطلوبه منا، بس اللي بهمني نعرف انه البيتا deflected والالفا and beta are deflected in the magnetic field, right? But البيتا deflects more. طبعا this is beta minus، صح؟ البيتا بلس راح تكون بنفس الدايركشن تاعت الالفا. Okay, again guys, البيتا deflects more than الالفا because has less mass. هلا let's talk about the decay finally, but just give me 1 minute. هلا guys, the decay الالفا when an alpha decay is taking place like this is a general rule for alpha. If I have a parent nucleus decays alpha, النيوكليوس الدوتر nucleus ايش بصير فيها يا جماعه؟ Z is decreased by 2 والatomic number is decreased by what? 4, right? عشان بالاخير ايش؟ الماss number والatomic number before must be equivalent to the mass number and atomic number where after, right? Any question about that? لا الفا ديكي طبعا بيكون بهالطريقه. هلا البيتا حكينا اتفقنا احنا عندنا 2 بيتا او 2 ديكيز. طبعا لازم تعرفوا هذا الاشي، بيتا بلس وبيتا ماينس. البيتا بلس كيف بصير؟ طلع معي. Sometimes guys one of the protons decays to neutrons. As a result of that شو بصير يطلع لنا؟ بيطلع لنا ايش؟ بوزيترون، وفي شيء بسموه نيوترينو. هذا رح نحكي عنه later on. هذا it's called ايش؟ نيوترينو. If beta minus is emitted, this means that the neutron decays to proton. Okay? Here, if beta minus is emitted, معناته this means that the neutron is decayed to proton. وهير ايش بيطلع لنا؟ بيطلع لنا electron, و this is called antineutrino. طبعا الجاما, as what we mentioned before guys, الجاما something excited بنحط لها star زي هيك. This excited the nucleus guys. طلع ما في عندنا change، يعني البيرنت والدوتر same nucleus، بس except انه this nucleus was excited, then it emits this gamma in order to become more stable or less excited. Okay. Let's now talk about the nuclear equations. هلا nuclear equations guys have certain things that must be conserved during any nuclear reaction. First of all guys, I think you are familiar with that. Mass number before, and mass number before a reaction or a nuclear reaction is must be equivalent to the mass number to the products after the reaction. Right? Also, the atomic number before for reactants must be equivalent to the atomic number for the products. Okay, so basically we can use this to predict the element that will be produced after this nuclear reaction. Hello guys, you have to memorize these things. Alpha, the atomic number is 2, the mass number is 4, or it might be written as helium 2,4. Beta, I have two types, -1, 0, +1, 0. You have to memorize this stuff, guys. Or it might be written as electron or positron. Gamma has 0, 0. Proton has 1, 1, and neutron 0, 1. You have to memorize these things. Okay. Okay. So I can use it to predict the daughter nucleus or the products. Here we are given a radon gas. This radon gas emits helium or alpha particle. or as a result of this radiation, guys, as a result of this radiation, here we have unknown element. Let's say it's X. I can predict the atomic number and the mass number of this element. So by using the periodic table, I can determine this element. So here, guys, this is 86. So the atomic number after must be 86. So if this is 2, this would be 84, right? 84 plus 2, 86, which is equivalent to 86. As well here, guys, we have 220. First one is 4. The second one must be 216. 216. So in this way, guys, the atomic number before is equivalent to the total atomic number after. The mass number before is equivalent to the mass number after. I think all of you are familiar with these things. So by finding the atomic number using the periodic table here, guys, I can similar thing, guys, here. مثلا, for example, if I have carbon 14, the carbon 14, guys, emits beta minus. So the daughter nucleus after this decay is nitrogen 714. Guys, if you compare the atomic number of the reactants with the atomic number of the products, they must be the same. Or similar thing if you compare the mass number for the reactants مع mass number of the products. And here, if I calculated 7 minus 1, 6, which is equivalent to the atomic number before. Here 14 plus 0 is 14, which is equivalent to the mass number before the nuclear reaction. We might be given a question like this, guys, and we are asked to predict what is the particle, or predict the particle that will be emitted after this decay. Here, guys, 83, right? So here must be 2. Here 218, 208, so this must be 4. So the particle here, guys, is alpha. Why? Because I have to memorize these things. Alpha has mass number 2, or atomic number is 2, or mass number is 4. And these things, I think also these things were covered in the previous year. Now, this is an important thing. This is the new thing that we have to discuss today. Conservation laws and nuclear reactions. Or first one, conservation of a nucleon, conservation of charge. Conservation of nucleon, guys, means conservation of mass number, because number of nucleons must be conserved, so mass number must be conserved. Conservation of charge, this means that proton number is conserved, right? Or atomic number is conserved. So the number of protons for the reactants must, total number of protons for the reactant must be equivalent to the total number of protons for the products. Conservation of momentum, right? Now, the new thing that I have to introduce today, it's the conservation mass and energy. In the previous time, guys, in the previous times, or even in the classical mechanics, energy is conserved. Energy is conserved, which means, guys, that the energy input must be equivalent to the energy output. The total energy input must be equivalent to the total energy output. Einstein found something new at that time. He found that, guys, it's not a conservation of energy, it's the conservation of mass energy. Yani he found a relation between the mass and energy, and I think you are familiar with this formula, which is E equals mc delta square, mc squared. Here, guys, using this equation, Einstein claimed that we can convert any mass to energy and vice versa. We can convert any energy to mass. So basically, he used the energy and the mass as a one quantity. And in quantum mechanics يعني خلينا نقول هيك roughly speaking we can use energy will mass as one quantity because they can be changed from each مثلا mass can be changed to energy or energy can be changed to a mass using this formula. So here guys I can say roughly speaking سريع guys انه احنا بالكلاسيكال ميكانكس حتى اللي كنا we consider it بالprevious units انه الماس is conserved والenergy is conserved يعني total mass n لازم يساوي total mass out وهذا حكينا عنه بالrate of flow if you remember انه total mass n equals total mass out total energy n equals total energy out. This is the conservation of mass this is the and the conservation of energy respectively. Now guys at the molecular level we can find something at that time was very strange انه mass changes. So basically guys and I can say now we have something called conservation of mass and energy or mass energy which means انه mass and energy can be used as a one quantity او as the same quantity. هلا رح نشوف هذا الشيء. فمعناته انا بقدر احكي انه mass and energy sum of mass and energy before is equivalent to sum of mass and energy after. يعني هلا we have to consider the mass and energy as a one unit. Let me show you this. Guys, one of the obstacles that the scientists at that time faced. طلع معي هون هلا. Guys, هلا here there is a nuclear fusion. Nuclear what? Fusion. In this nuclear fusion, look to the masses here. We have something called deuterium with tritium. They fuse together. يعني صار combining for these. As a result of this reaction, we got helium and a neutron. Guys, look to the total mass before or look to the total mass after. The total mass before, no matter the unit, during this nuclear reaction, if you notice here, if we consider the mass changes here, the mass of the product of the reactants, which are deuterium and tritium, were 5.0301, no matter the unit. After the reaction, I found that it becomes 5. The total mass of the products 5.0113. So there is a change in mass here, guys. There's a change in this mass. The classical mechanics was not able to justify this change in mass, but in quantum mechanics we consider that this amount or this change of mass converted to energy, right? Or the difference between the mass between the reactants and the products changes to energy. Okay, يعني الفرق بهذا الماس راح ل energy. فهلا صارت عندنا الكونسبت انه الماس والenergy seems that they are the same or we can consider them as the same physical quantity. Generally in both chemical and nuclear reactions some convergence between rest mass and energy occurs. The products generally have smaller or greater mass than the reactants. In general, the total energy must be conserved. The missing rest mass must therefore reappear as kinetic energy released in the reaction. Okay, guys? طبعا nuclear binding energy هاي لا مش مطلوبة منا صراحة. يعني بس هي it's related to this difference in mass. Okay, it's related to the difference in mass. Here we have to define something called electron volt. electron volt, guys, it's an energy used, or this unit of energy is used for molecular levels. يعني like electrons والprotons وهي الأشياء, they use electron volt instead of the joule, because the joule will be extremely high compared to the energies of the particles at the molecular level. Hello, what is meant by 1 electron volt? Guys, again, electron volt, it's a unit for energy. It will be used for a molecular level or atomic level, like the energy of electrons, protons, nuclei, atoms, whatever, beam of neutrons or something like this. Hello, what is the definition? If I place an electron, let me remind you by this. These are two parallel plates connected to a potential difference. This potential difference, guys, 1 volt. This is negative, this is positive. Well, I placed electron here. So an electron will move in this way. If you remember, guys, we calculated the energy for a charge inside a uniform electric field as Q times V. Q times V. What is the Q here? It's the charge of electron. The voltage here is 1. So the energy needed to accelerate this electron between negative plate to positive plate is 1.6 times 10 to the power minus 19 joules. Right? This is the energy needed for the electron to be accelerated in uniform electric field as a result of 1 volt potential difference. This amount of energy, guys, this amount of energy, it's called 1 electron volt. Okay, 1 electron volt. يعني simply, 1 electron volt is 1.6 times 10 to the power minus 19. Okay? This is used for microscopic scale as an energy of unit, as an energy unit. يعني guys, it's easy. مش كتير صعب الموضوع. الكونسبت انه كان عندنا unit اسمها joules. هلا we will use another unit for energy, but for microscopic scale, يعني for the level of electrons, protons وهاي الاشياء, molecular level or nuclear level. هاي الانرجي او هاي ال 1 electron volt is equivalent to 1.6 times 10 to the power minus 19. هلا sometimes we used or we will use اللي هي mega electron volt, MEV. ال MEV, guys, هي 1 times 10 to the power 6 electron volt. Right? Mega, you know that. And 1 times 10 to the power 6 what? Electron volts. We may use also giga electron volt. Giga electron volt 1 times 10 to the power 9 electron volt, and so on. Let's talk about the atomic model. Before, guys, before our well-structured atomic model, at that time we had several models for the atoms, because you know that the atoms cannot be seen by our eyes. At that time the scientists, or even by instruments or whatever, at that time, guys, the scientists start thinking about models that can be used to study the atomic structure. One of these models was called Blom Budding model of the atom. This model, guys, like this, it's you took that على فكرة بالأو level, by the way. We have here cloud of positive charge. This cloud of positive charge, guys, dotted by the electrons. يعني like the bonding أو the Blom bonding, يعني أو حتى زي watermelon or something like this. Okay, guys, this was the previous model that was formed by scientist who's called Thomson. هلا بتعرفوا انتوا يعني الساينتست اجى واحد اسمه رذرفورد، يعني بحبوا دائما يتفلسفوا وكذا ويحطوا التاتش بتاعهم. فرذرفورد at that time wanted to test this. test this experiment. شو عمل Rutherford? Let me show you this.
Rutherford's model
Guys, this is an important video because guys, here we have frequent questions about the Rutherford model. هلا in Rutherford models guys, طبعا هلا after this about this model, and here we have to focus on two things guys: the observations that Rutherford made and the conclusions also that Rutherford also made.
of an atom. Rutherford's scattering experiment. In 1911, Rutherford performed an experiment in which he bombarded a thin foil of a heavy metal like gold with a team of fast-moving alpha particles, which are doubly ionized helium ions, He2+, each having 2 units of positive charge and 4 units of mass, 4U. These were obtained from radium placed in the cavity of block of lead.
Let's talk about the setup first of all. Here guys we have a source, alpha source. This alpha source produces alpha particles. These alpha particles are like this. This is alpha source. Okay, this is a very thin gold foil, very thin gold foil. Okay, he selected. We will discuss. We will discuss later why did Rutherford select alpha to carry out this experiment. Hela, this is a photographic film. Guys, another word. Sorry, it's not photographic film. It's fluorescent film. Sorry, fluorescent film. It acts as a photographic film, or it has the same behavior. This fluorescent film, guys, will give us a spotlight like this when alpha particles interact with it. Okay, when alpha particles interact with it. Any question about that, guys? Fluorescent film. طيب, let's complete.
And made into fine beam with a slit. He observed the scattering of the rays after hitting the foil by placing a circular zinc sulfide screen around the metal foil. Wherever alpha particles struck the screen, a flash of light is produced at that point on the screen. That the heavy body present in an atom must be occupying a very small volume. From these experiments, Rutherford made the following observations.
These guys are very important. You will be asked about them. Pay attention, please.
Most of the particles, that is 99.9%, passed through the foil without undergoing any deflection. Some particles were deflected through small angles.
Things here. Some small deflection.
And a few were deflected through large angles. Very few, only 1 in 12,000, were deflected back, that is, through an angle greater than 90 degrees. From these observations, Rutherford drew the following conclusions.
Here we have mainly 3 or 4 observations. Guys, pay attention to the way that you will write these observations in the question especially. Most of alpha particles are not being deflected. Some of alpha particles deflected through small angles. Few of alpha particles are deflected also through a large angle. Very few of alpha particles are bounced back or were bounced back. Okay, these are the observations that Rutherford observed. Now let's talk about conclusions according to these observations.
Since most of the alpha particles passed through the foil without undergoing any deflections, there must be sufficient empty space within the atom. This small, heavy, positively charged body present within the atom was called nucleus.
Guys, you know that at that time,
Rutherford.
You have to pay attention to this, guys. At that time, no anyone knew that والله في عنا nucleus protons neutrons electrons لسه كان يعني they don't have, at that time they did not have any information about the atom or the atomic structure at that time. Pay attention. From this experiment, he deduced or he concluded or he drew a conclusion that there is a small, listen, a small size heavy positively charged object وسماه nucleus, right? It's called what? A nucleus. From his observations.
Rutherford's nuclear model of an atom. On the basis of scattering experiments, Rutherford put forward a model of atom known as Rutherford's nuclear model. There is a positively charged center in an atom called the nucleus, in which all the mass of an atom resides. The size of nucleus is very small as compared to the size of an atom.
Second conclusion.
The electrons revolve around the nucleus in well-defined orbits. As some of the alpha particles were deflected by small angles, and since alpha particles are positively charged, they could be deflected only by some other positively charged body present within the atom. The alpha particles which deflected through small angles were those which passed far from this positive body. The alpha particles which deflected through large angles were those which passed close to the positive body. Since some alpha particles were deflected back, alpha particles are heavy particles, they could be deflected back only when they strike heavily inside the atom. Since number of alpha particles deflected back is very, very small, which shows that the positive charge and mass of gold atom must be occupying a very, very small volume. Drawback of Rutherford's model.
Okay, guys, is that clear now? So Rutherford, طبعا you might be asked about the experiment, observations, and what the conclusions. Okay, guys. Here there's a question: why are alpha particles were chosen at that time? There are several reasons for that, guys. First of all, alpha particles, if you remember, or as what we discussed in the previous time, they have a discrete values of energy, not a range. Yani, let's say available energies for alpha particles either 10, 20, 30, 40 quantized only. They will not be affected by an orbital electrons since they have a large momentum. ليه؟ لأنهم massive. طبعا massive compared with other radiation and moving fast. Also they have a large charge. Beta particles have a range of energies, guys, and they can be deflected by orbital electrons. This is why alpha particles are used, but beta particles or alpha particles were used, sorry, while beta particles were not used. Guys, you will be asked about these things, and you will be asked why are alpha particles were used while beta particles were not used. Any question? موضوع الرينج اوف انرجيز تمام ما راح يعطيني definite observations. يعني شو definite observations? If you go back to the video right here, بس خليني افهمكم شو قصدي. مثلا هون عندنا 3 main observations. تمام 1 2 3 صح هدول هم المين things. هل كان في عندنا range of energies معناته انا راح اشوف هون كمان سبوت وهون سبوت وهون سبوت وهون سبوت وهون سبوت وهون سبوت وهون 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 صح ولا لا؟ You got my point? So if I have a range of energies, guys, I may have several observations which may not help me to draw a good conclusion. بس لما يكون عندنا values أو specific values for the energy of alpha particles معناته أنا I have only 3 مثلا or 4 possible observations that I may observe. One at large angle, one at small angle, one bounces back. فبصير هيك بصير الأمور to draw conclusion much easier than range of energies. The other important thing, guys, إنه البيتا أصلا will be deflected by orbital electrons. It will not give us any information about the nucleus لأنها it will not reach a nucleus. يعني هي ما راح توصل للنيوكليوس هي بس توصل outer shells of electrons will be deflected. It will not show me anything about the nucleus أو about the atomic structure. طبعا Rutherford حكينا most of fast highly charged alpha particles went straight through undeflected. Some of alpha particles were deflected back through large angles. A very small number of alpha particles were deflected backward. This was definitely not expected by Rutherford. Just a second. طيب بس مش راح اطول جماعه بس خليكم اخلص الكونسبت تبع راذرفورد وبنشوف بعدين شو بدنا نسوي. تمام فيعني الكونسبت او انا هي حطيت لكم اياها هون ايش لازم نعمل او شو لازم نكتب. هاي 3 observations as what we mentioned in the او حتى as we discussed before وهي for each one we have a proper conclusion. Okay طبعا here we have it should be a massive. The nucleus has a large positive charge when repelled back. أيوة massive nuclei. Okay خلاص fine. This is also what was discussed in the video, guys. You know, if alpha particles, guys, are away from the nuclei, they went straight without any deflection. If they are very close to the nucleus, it will be deflected like this. Guys, if this is called, this angle is called angle of deflection. Angle of deflection. Right angle of what? Deflection. Here, if it's very close, it will be deflected through large angle. If it's head on to it will be deflected back like this. If it's or if it's in the direction to hit the nucleus. طيب guys بهذا التوبيك بس خليكم معي. I need بس only 10 minutes. تمام 10 minutes or I will stop. Okay, بكون خلصت ال radioactive material. هلا رح نحكي عن the classification of particles. هذه ال classification of particles guys هي memorizing stuff, not more than that. يعني بس we have to memorize these issues. We will not go deeply in the standard model. Pay attention to this. This was added to the syllabus, or this topic was added to the syllabus since 2016. Here, guys, the matter consists of atoms. Atoms consist of nucleus and electrons. Nucleus consists of protons and the neutrons. The new thing, guys, here, each neutron and proton consist of something called quarks. Right? Consist of particles that are called what? Quarks. So all the particles in the universe, especially tiny particles, are classified like two main categories, or categorized to two main categories: leptons وhadrons. طبعا انا بعرف اني عم بحكي اشياء كثير غريبه، بس anyway they are called like this: leptons وhadrons. Hadrons also can be classified to mesons and baryons. Let me complete. These are, guys, the quarks, or this is called standard model. Standard model, guys, اتفقنا انه الprotons والneutrons consist of quarks. طبعا there are another particles that consist of quarks, but we will not talk about them. Hello, what you have to know about these things, you have to memorize them, and you have to memorize the charge of each one. Quarks عندنا ايش؟ up, down, charm, strange, top, bottom. هلا طبعا في يعني there are reasons, guys, طبعا مش scientific reasons حتى even, there are reasons why are they called like this, بس هذا مش موضوعنا. لا هم يا
استاذ
ليبتونز
هلا مش في
يا
غير
هادرونز.
الليبتونز
خلي شوي اسمع اذا بدكم، بس خليني اكمل،
والهادرونز كمان.
واللي حابب هيك اشياء زياده
لا
مثلا
في كمان
بعد الحصه بقعد انا وياه ونشرح الاشياء اللي اي سؤال ثاني برا التوبيك بنحكي فيه، لانه هذا التوبيك كثير ديب وبده. فاذا اتفقنا what we have to memorize ال up down charm strange وtop وbottom. التشارج تاع هذا الرو 2/3e، والتشارج تاع هذا الرو -1/3e. طبعا for each quark, guys, there is an anti-quark. Like as what we mentioned before, guys, any antiparticle has the same mass of the particle, but it has opposite charge. Okay. Now let's distinguish between leptons and quarks. Leptons and quarks, guys, are called fundamental particles. What does this mean, guys? They cannot be divided to a smaller units. يعني كأنهم basic things. يعني leptons cannot be divided to any other smaller particles. والquarks as well. فهدول بسموهم fundamental particles. يعني the smallest particles that can be found in the universe. هلا leptons شو هم leptons؟ طلع معهم. عندنا leptons هم electrons, ميون وتاو. الكترون، ميون وتاو، هدول بنسميهم ليبتونز. طبعا each ليبتون بيجي معاه شيء اسمه نيوترينو. تمام؟ اي ليبتون بيجي معاه ايش؟ النيوترينو. طبعا you have to memorize التشارج. التشارج تاعت الالكترون والميون والتاو -1، وكل واحد من هدول الليبتونز بيجي معاه شيء اسمه نيوترينو، بيطلع معه دائما. هلا حكينا عن الكواركس. تمام؟ Another difference, guys, between the leptons and the quarks is that leptons can exist on their own. The quarks لا. يعني no way, guys, to find free quarks. يعني تلاقي هيك free quark ماشي لحاله. لا، لازم يكون bound مع other quarks. هذا كتير مهم البارت اللي هو الفرق بين الهادرونز والليبتونز. الهادرونز guys the heaviest particles, these things that will be asked about it, split up to baryons and mesons. They subject to the strong nuclear force, or they are not fundamental particles. هلا I will not go in details about what is meant by strong nuclear force or weak nuclear force, because it's not in our syllabus. But we have to know this as a basic thing. And hadrons are subject to a strong nuclear force. They are not fundamental. They are the heaviest. هلا شو الفرق بين الباريونز والميزونز؟ الباريونز دائما بيكون consist of 3 quarks. دائما الباريونز فيهم كم كوارك؟ 3 quarks. كله حفظ يا جماعه، يعني هذا كله it's a memorizing stuff. مين عندنا باريونز؟ بروتونز وايش؟ ونيوترونز. تمام؟ الليبتونز، هلا الليبتونز شو لازم نعرف عنهم؟ انهم the lightest particles. تمام؟ وهم they are subject to ايش؟ ايش؟ weak nuclear force. هلا قلنا ما رح نحكي شو يعني weak و strong، مش موضوعي، بس موضوعي اعرف انه الليبتونز هم lightest particles وهم they are subject to a weak nuclear force. مين هم الليبتونز؟ electrons ميون ونيوترينو وتاو. نسينا نحط التاو. إشي تاني لازم نعرفه، البروتون consist of what؟ البروتون guys consist of 3 quarks. Up, down. You have to memorize these things. Up, down. التوتال charge تاعت الأب 2/3 2/3. So if I add the charges guys 2 ب 2/3e plus minus 1/3e، فالاوفر قديش بيعطيني؟ 1e. وهذا you'll be asked about it guys. النيوترون برضه بس لنكون النيوترون هو ايش؟ up down down up down down. If I add their charges اللي هم الكواركس راح يعطيني zero charge as expected، لانه نيوترون as يعني جماعه هون ما راح اروح بتفاصيل كثير، كل اللي بيهمني نعرف شو يعني هادرونز، ليبتونز، شو هم الكواركس بس كبيسك كونسبتس، البروتون كم كوارك فيه وايش هو، والنيوترون كم كوارك فيه وايش هو. تمام؟ اخر اشي بهذا التوبيك اللي هو عندنا البيتا ديكي، بيتا بوزيتيف ديكي وبيتا نيجاتيف ديكي. ناخذ اول شيء البيتا نيجاتيف ديكي بس دقيقتين. هلا يا جماعه عندنا بيتا ماينس ديكي وعندنا بيتا بلس ديكي. البيتا ماينس متى بيصير؟ اذا عندنا نيوترون تحول لبروتون. تمام؟ نيوترون اللي هو 0 1 اعطاني بروتون والكترون، واتفقنا مع اي الكترون بيجي انتي نيوترينو. انتي ايش؟ نيوترينو. تفرجوا كيف هذا الاشي بيصير in terms of quarks. هلا البروتون النيوترون ايش هو؟ هو داون داون اب، صح؟ تحول لايش؟ لاب اب داون زائد ايش؟ الكترون زائد انتي نيوترينو. يا جماعه يعني شو اللي صار فعليا in terms of quarks؟ انه واحد من الداونز decay to up، صح؟ هذا اللي لازم نعرفه، بس انه الداون صار up. as a result of that شو اعطاني؟ اعطاني الكترون وانتي نيوترينو. هذا بسموه weak nuclear reaction. weak nuclear reaction. تمام؟ البيتا بلس تفرج معي برضو اشي بسيط. بروتون عشان يطلع معي بيتا، يعني عشان النيوكليوس هاي to decay beta one of the protons decays to neutron plus positron plus neutrino. تمام؟ يعني واحد من البروتونز بيعطيني نيوترون بضل جوا النيوكليوس، واللي بيطلع برا النيوكليوس مين هو؟ البوزيترون مع نيوترينو. طبعا البروتون 1 1 نيوترون 0 1. لو اخذناه in terms of quarks بسيط. البروتون هو up up down هيعطيني down down up بلس البوزيترون بلس النيوترينو. فعليا جماعة هو ايش اللي تغير؟ الاب صار داون. الاب اعطاني داون بلس بوزيترون بلس نيوترينو. Guys, this is all what you have to know about the standard model.